Hurricanes stand as formidable and destructive forces of nature, unleashing immense power upon coastal regions and beyond. Their sheer scale and intensity demand our attention and respect. Understanding these atmospheric giants is not merely an academic exercise. It is crucial for safeguarding lives and property. The crucial need to understand their formation, behavior, and impact cannot be overstated. These insights are vital for both immediate safety and long-term resilience against their catastrophic potential. Hurricanes are far more complex than simple windstorms, involving intricate scientific principles. Their complexity encompasses a vast array of meteorological and oceanographic phenomena. Scientific principles governing fluid dynamics, thermodynamics, and atmospheric pressure all play a critical role in their genesis and life cycle. These storms are living examples of Earth's powerful energy systems at work. Beyond the science, geographical factors significantly influence their trajectories and intensity. The warmth of ocean waters, global wind patterns, and landmass configurations all dictate where and how strongly a hurricane develops and moves. Their paths are shaped by a delicate balance of forces. Ultimately, hurricanes pose a significant and recurrent threat to human life and critical infrastructure. Their capacity for widespread destruction necessitates a deep, comprehensive understanding across all levels of society. This knowledge empowers us to prepare, respond, and rebuild more effectively. At their core, hurricanes fundamentally operate as giant heat engines. They draw energy from the vast thermal reservoir of the tropical oceans, converting heat into devastating winds and torrential rain. This process drives their impressive power and destructive capabilities. Their formation occurs exclusively over warm ocean waters, typically with surface temperatures exceeding 26.5 degrees Celsius or 80 degrees Fahrenheit. This specific thermal condition provides the essential fuel for their development, acting as the critical starting point. Without warm water, they cannot sustain themselves. These powerful systems typically originate near the equator, within latitudes roughly 5 to 30 degrees north or south. Here, the ocean surface consistently receives strong solar radiation, maintaining the warm conditions necessary for tropical cyclone formation. The tropics serve as their breeding ground. The process begins with the sun's energy heating the ocean surface, which then warms the air directly above it. This initial heating is the first step in creating the thermodynamic imbalance that will eventually power the storm. It sets the stage for a chain reaction. As the surface air warms, it becomes less dense and begins to rise vigorously. This upward movement of warm, moist air is a key component of hurricane genesis. Carrying latent heat into the upper atmosphere, it creates a powerful convection current. This rising air creates an area of lower atmospheric pressure at the ocean surface beneath it. As more air ascends, the pressure continues to drop, drawing in surrounding air, which then also warms and rises. This establishes the foundation of the storm's circulation. As the ascending air cools due to expansion in the upper atmosphere, its moisture condenses. This condensation releases an enormous amount of latent heat, further warming the surrounding air and causing it to rise even faster. This positive feedback loop intensifies the storm. The continuous condensation of moisture leads to the formation of towering thunderstorms, arranged in a spiral pattern around the low-pressure center. These thunderclouds are the visible manifestation of the hurricane's energy release. Often reaching great heights, they act as the storm's engines. Simultaneously, Earth's rotation, known as the Coriolis effect, induces a spinning motion in the inwardly flowing air. This force deflects the air to the right in the northern hemisphere and to the left in the southern hemisphere, initiating the characteristic cyclonic rotation. It's a fundamental physical principle at play. This rotation eventually leads to the characteristic swirling structure that defines a hurricane. The entire system begins to organize around a central point, developing into the recognizable vortex we associate with these powerful storms. The spinning motion is essential for hurricane development. Hurricane strength is quantitatively measured by the Saffir-Simpson Hurricane Wind Scale. This classification system provides a standardized way to communicate the potential impacts of a storm based on its sustained wind speeds. It is a critical tool for public safety and emergency management. The scale categorizes tropical cyclones that reach hurricane intensity into 5 distinct levels, each corresponding to a specific range of sustained wind speeds. This categorization helps differentiate between weaker storms and those capable of extreme devastation. Each category represents a significant increase in potential damage. Category 1 storms are considered the weakest on the scale, with sustained winds ranging from 119 to 153 kilometers per hour, or 74 to 95 miles per hour. While still dangerous, they typically cause limited damage to well-built structures. Their impact can still be significant. In stark contrast, Category 5 storms are the most powerful and feared, boasting sustained winds of 252 kilometers per hour or 157 miles per hour or greater. These storms represent the absolute peak of hurricane intensity, capable of unfathomable destruction. They are truly catastrophic events. Indeed, Category 5 hurricanes are capable of catastrophic damage, often flattening homes, destroying infrastructure, and causing widespread long-term power outages. Their extreme winds can tear apart robust buildings and reshape landscapes. Recovery from such storms can take years. Within the swirling mass of a hurricane lies a unique feature known as the eye. This central region is typically the calmest part of the hurricane, characterized by light winds, clear or partly cloudy skies, and sometimes even a glimpse of the sun. It is a stark contrast to the surrounding storm. Encircling this calm eye is the eye wall, a formidable ring of intense thunderstorms. This part of the hurricane is the most dangerous, housing the strongest winds and heaviest rainfall. The eye wall is where the storm's most destructive energy is concentrated. The eye wall experiences the hurricane's most intense winds and heaviest rainfall, posing the greatest threat to anything in its path. Structures hit by the eye wall are subjected to the full fury of the storm. Its passage signifies the peak of a hurricane's destructive power. The impact of a hurricane extends far beyond the immediate damage caused by wind and rain. Its destructive forces ripple through communities, affecting various aspects of life and environment. Understanding this multifaceted impact is crucial for comprehensive preparedness. Perhaps the most insidious and often deadliest aspect of a hurricane is the storm surge. This phenomenon is an abnormal rise in sea level generated by the storm's powerful winds pushing water towards the shore. It can inundate vast coastal areas rapidly. Storm surge, combined with normal tides, can cause devastating coastal flooding, submerging homes, roads, and vital infrastructure. The sheer volume and force of this water can be overwhelming, leading to extensive property damage and loss of life. It reshapes coastlines dramatically. Beyond storm surge, widespread inland flooding is also a significant threat caused by the heavy and prolonged rainfall associated with hurricanes. These torrential downpours can quickly overwhelm rivers, drainage systems, and low-lying areas. This can lead to flash floods and riverine flooding. Such flooding can displace communities, destroy crops, contaminate water supplies, and cause severe soil erosion. The aftermath often includes long-term environmental and health challenges. It presents a major obstacle to recovery efforts. Furthermore, hurricanes can spawn tornadoes, adding another layer of destruction to their already formidable arsenal. These short-lived but intense rotating columns of air often form in the outer rain bands of the hurricane. They can appear suddenly and without much warning. These tornado outbreaks contribute further to the overall destruction, tearing through localized areas with extreme winds. They add complexity to disaster response, as communities must contend with multiple types of severe weather simultaneously. The combined impact is truly devastating. Climate change is increasingly influencing hurricane behavior, leading to concerning trends in their intensity and impact. The warming planet is altering the conditions that govern these powerful storms. This global phenomenon requires our urgent attention and adaptation. Warmer ocean temperatures, a direct consequence of climate change, provide more energy for hurricane development and intensification. This additional heat acts as extra fuel, potentially leading to more powerful and longer-lasting storms. The oceans are becoming hotter engines. Rising sea levels, another critical impact of climate change, significantly exacerbate the threat of storm surge. Higher baseline sea levels mean that even a moderate storm surge can penetrate much further inland, increasing coastal vulnerability dramatically. Coastal communities face an amplified risk. While the total number of hurricanes may not necessarily increase across all basins, their intensity and overall destructive impact are likely to worsen. We are seeing a trend towards fewer but stronger storms, particularly major hurricanes. This shift in intensity poses a greater threat. Given these intensifying risks, the importance of preparedness for mitigating consequences becomes paramount. Proactive measures, from individual household plans to large-scale infrastructure projects, are vital for protecting lives and minimizing damage. Preparedness is our strongest defense. An essential role is played by early warning systems, which provide crucial time for communities to prepare and evacuate. Advanced meteorological forecasting and communication technologies are indispensable in disseminating timely and accurate information. These systems save countless lives. Necessity drives effective evacuation plans, ensuring that vulnerable populations can move to safety before a storm strikes. Well-rehearsed routes, designated shelters, and clear communication are key components of a successful evacuation. Planning ahead is non-negotiable. The importance of building codes designed for hurricane-force winds cannot be overstated in minimizing property damage. Stronger construction standards, fortified roofs, and impact-resistant windows are critical for making homes and businesses more resilient. Infrastructure must be built to withstand these forces. Through these combined measures, robust warning systems, effective evacuation, and resilient construction, we aim to protect lives and property. These actions represent a comprehensive approach to living with the persistent threat of hurricanes. Safety is the ultimate goal. A crucial investment in resilient infrastructure is fundamental to future hurricane preparedness. This includes elevating roads, strengthening power grids, improving drainage systems, and constructing natural barriers like dunes and wetlands. Long-term planning is essential for community survival. Building resilient communities against hurricane threats involves not just physical infrastructure, but also social cohesion and emergency planning. Empowering individuals and local governments with resources and knowledge fosters a collective ability to withstand and recover. Community strength is paramount. Ultimately, the vital role of understanding hurricane science empowers us to face these challenges effectively. Knowledge of their formation, behavior, and potential impacts informs all our preparedness efforts. Science provides the roadmap for resilience now and in the future. Therefore, taking proactive measures, guided by scientific understanding, is crucial for navigating the complex and escalating challenges posed by hurricanes in a changing climate. Our collective action today will determine our ability to endure these powerful natural phenomena tomorrow.